Okay, dear participants, it's time to start the practice. And it's my pleasure to introduce you our next speaker, Kristina Frizyuk. Kristina has graduated Peter the Great St. Petersburg Polytechnic University with a bachelor's degree and St. Petersburg Academic University with master's degree. And Kristina is currently a second-year PhD student at the ITMO University. She's been teaching general physics at ITMO University and also quantum optics at the academic university for a couple of years. She has won several grants and numerous awards for conference presentations and also Olympiads in physics and math. She had a scholarship at the Karlsruhe Institute of Technology in Germany last year. Her current research interests include multipolar decomposition and nonlinear phenomena in nanophotonics. So please welcome Kristina with practice on exact multiple decompositions with applications in nanophotonics.
Ola, thank you for the introduction. And okay, on this practice, feel free to switch on your microphones and ask some questions. And if something went wrong, goes wrong, I will prohibit switching on the microphones, but it's okay now. And you will need materials which are on the Google Disk. I send the link to the Telegram and also to the chat. You can download. Here is the PDF file which is related to the practice, and two files which you're going to use in Matlab. So you will need only Matlab for this practice. Well, I will wait a little bit for you to download it. And PDF file, you will only need it if you skipped something or after the practice, because I will also show all information on the screen. First of all, I will remind something which you probably already heard from Andrei, from Ivan, and I will introduce some notations, and they will move to the working in Matlab. Okay, and first of all, I would like to remind how the scalar spherical functions look like. Here is two numbers, J and M. Sorry, wait a minute. Two numbers refers to angular momentum and projection. Here is the square root, which refers to the normalization, and we will not pay much attention to these coefficients. Here is associated Legendre polynomials, and here is exponential multiplier, just dependence on the angle phi. And I would like to pay your attention to the Cartesian, to particular functions with angular momentum equal 1, and in Cartesian coordinates, they are connected by this way with z, x, and y coordinates. You will need it if you, for example, want to find the relation between something spherical and Cartesian. And then we will use two types of vector spherical harmonics. here is first type is the same as Ivan introduced. They are related to the scalar spherical functions. And we have 3 times: magnetic, electric, and longitudinal. And note that they only depend on angles of vector r. Here, actually, they only depend on theta and phi. And they are not depend on r. This is the first type of vector spherical functions. So these are only have transverse components, and this only has longitudinal component. And the second type of vector spherical functions, which are exactly which are in meteory. You can see them in meteory, and Andrei talked about them. These are solutions of vector wave equation, and the difference between these 2 types is just actually they have a similarity, because this magnetic harmonic is proportional to this magnetic harmonic, but here we can see a Bessel function. So they don't depend only on theta and phi, they also depend on r, theta and phi. And electric harmonics, which are just curl of magnetic harmonics, and they are produced the same way as this harmonics, but instead of spherical function, instead of scalar spherical function, you should put here these psi functions, which are just a product of some kind of Bessel function to scalar spherical function. So, and these are used in meteory, and you maybe had a question, because on a Andrei lecture, you had used some quite different notations. You had, for example, these kind of functions, and this, which are even, which are odd. And the same as for electric, you had even and, and odd harmonics. But the connection between this kind of harmonics and this are actually very simple, because I would like to remind that spherical functions has the exponential term here. And in case if you introduced even and odd functions, you have, instead of exponential function, you have cosine and sine. So this is, and then you can find a simple connection between these functions, which only 2 indexes, and these functions with 3 indexes. And they are just connected the same way as sine and cosine. And I can actually call this one complex and this one real. And sometimes it is more comfortable to use real functions. For example, in simple Mie scattering, which you had in Bohren-Huffman. And sometimes you're better to use complex functions just because, for example, if you have circular polarization or something like this, all the chirality stuff and so on. So you just change the basis, and in some different bases, different notations are more convenient. And the one more reason you can sometimes have real spherical functions, and that you can simply draw them, because you can draw any real vector spherical function. You can draw them with help of mathematical code, which Andrew sent to you and yesterday, and by some different method. And they just look like not exactly the same as scalar functions. Here are scalar spherical functions, but they have some connection with this. And I will go back to this picture later. Maybe, yes, I see the question. M refers to magnetic harmonics and N refers to electric harmonics. And in other type of spherical harmonics, X refers to magnetic and Z refers to electric. And actually here we have also longitudinal ones, which are L, but we will not use them now, but sometimes they're also useful. And actually two types of harmonics, as Ivan already mentioned, they are connected with some kind of Fourier-like transform. And you can also find this transform in the appendix of PDF file. And what is the main problem we will solve? Please imagine that we have some current distribution, and it can be actually any current distribution. For example, we have found induced current in some cylinder, in some nanoparticle, in some nanoparticle of any shape. And we know from, for some reason, for example, we have computed in using TST or COMSOL some induced currents inside the particle. So imagine that we know the currents, and then we know Fourier of the currents, and here I use K vector, but it is similar as Ivan used in lecture and called it momentum. And this was a lot about it on the lecture. This is only on a spherical shell. Then vector is equal omega over c. And what you have, imagine that you somehow decomposed the currents by this, guys, these three spherical functions. You can always do this because they are basis functions, and you know these coefficients somehow. And I would like to remind that this is electric, this is magnetic, and this is longitudinal one. So if you have such decomposition of a current, you can say, and you can prove that the field which is produced by such current, the far field, outside some spherical shell which is around your current, the field will be written by this formula. And only electric and magnetic harmonics are here because longitudinal doesn't pay any contribution. So we are not interested in them now. So, and these coefficients here before one kind of spherical magnetic harmonic, and here before another kind of electric spherical harmonic. They are just connected by some constant. Here is Z is impedance, and it is equal. Actually, in case of vacuum, it is equal to this. So if you have found somehow these coefficients, you can immediately find these coefficients. And actually, this is exactly what you need if you would like to make some multipolar decomposition of some field radiated by some current. I would like to remind for some people who came later that you can switch on your microphone anytime and ask some questions. And also you can write them in chat. Okay, for example, if you have some particle and some wave which is incident on the particle and some currents induced by inside this particle, and you know these currents, you can immediately get the scattering cross section, and it is easily connected with these coefficients. It's just a sum of the squares of absolute value of these coefficients. So the only thing you need to do is find these guys. Well, okay, and how to do this? You can do this by a formula, by these nice formulas. We will only speak now about a dipolar case. So J equal 1 and or angular momentum, which is L in Andrews notations, equal 1. But you will you can do absolutely the same thing for quadrupoles, octupoles, and so on. So this is a vector of these coefficients, and this equal to some integral with product of the current, because you know the current because you have computed it in COMSOL, and this is magnetic dipole. And this is electric dipole. And you can note that here you have X, Y, and Z, and here you have X, Y, and Z. And as you remember, here we had spherical indexes, but the connection between them you can find, for example, in the appendix. And also, actually here it is not needed by this. Some question? Maybe? Okay. In this formula, you don't have any spherical indexes. And if you write this formula in Cartesian coordinates, you obtain immediately these three Cartesian coefficients. Let's look at it more precisely. Here we have straight product, not a straight product, but vector product. And this is actually a vector. So under the integral, we have, for example, some vector function, which is, let us call it f. And it depends on some, for example, on spherical coordinates. And because this is a vector, we have three components. So we have, under the integral, we have something like this. And I would like to put it. So if you need to find a particular component, this, for example, x component, you need to integrate this term And if you need to find this component, you need to integrate this term. And if you need to find this component, you need to integrate this term. Because these guys, you can throw them out of the integral. And we will, first of all, consider only this. And then if we have time, we will also consider this. And then these formulas are exact. So if you find for some current these coefficients, they will be true for any size of your current, for any size of your nanoparticle, for any wavelength, and so on. And here you can easily obtain the approximate formula. For example, you took these Bessel functions and just decompose them. Imagine that you have very small nanoparticle. So this size A multiplied by a wave vector goes to 0. So under the integral, all this argument will be very small. So this is a limit, then goes to 0. And so you decomposed these Bessel functions, just put them into these two formulas, and immediately obtain the approximate formulas, which not contain Bessel functions. And now, actually, I would like to ask some question. It will appear now. Try to guess for which wavelengths the approximate formula works well if the particle's refractive index is equal 3 and particle's radius equal 200 nanometers. Do you see the question?
Yes, we saw it.
Mm-hmm.
Yes.
Thank you. Actually, for some reasons, I can't see any words. Maybe some Zoom problems. Oh, okay. I will just wait for some time, and then we should move further. Well, we will, this formula, I would like to remind one more time that this formula is correct for any possible current. So if you have any kind of nanoparticle, any shape of nanoparticle, you can apply this formula and obtain the field. And but we will apply it to a sphere just for reason that this current is given analytically. So we can obtain this current just from mean theory and put it into this formula, compute the scattered field and compare it with the results of mean theory. Has somebody voted? Could you please reply?
Yes.
Okay, maybe just, I don't know why there are no results. Something bad with Zoom. Actually, the right answer, you can check it later, is 750 nanometers. It's around this wavelength, this stops working. And the next question, you can actually, and if we have Mie scattering, we will consider, first of all, I would like to remind you that Andrew, for example, has considered a case. Then he had incident field along Z and polarized along X. And this is exactly which you can find in a Boren-Huffman's book. And you can find out that not every multiple is excited. You can find that not every M are possible. And the question is to choose which multiples are excited in such sphere. Oh, wait a minute, maybe. And the right answer is, in this case, only multiples which have M equal 1 are excited. And in case of magnetic dipoles, you can only excite odd multiples. And in case of electric dipoles, you can excite only even multiples. And this is due to the following fact that, let us look at these guys. Here you have magnetic, and here you have electric. And if you have X polarized incident wave, you can see that you of course will excite electric dipole along X, but magnetic dipole will be along Y, just because electric field of magnetic dipole is still somehow parallel to X. So electric field should always have a component which is along X-axis. And here it is still along X, along minus X. And for example, for quadrupoles, you have this kind of electric quadrupole. Here electric field is again along X and minus X, and magnetic field is also along X for magnetic quadrupole. And for all these guys, M equal 1. But the question is the following: can we somehow excite by plane wave multiples with M not equal 1? I think the questions doesn't work great. And you can try to answer them in chat. What should we do to excite? The question is, what should we do to excite multiples with M not equal 1? Please answer in the chat. Yes, have a circular polarization can be an option, but actually, in case of circular polarization, you should maybe use not real harmonics, but complex one. And in case of right-handed polarization, you will excite in circular polarization. In case of, for example, left-handed, you will have m equal 1, and for the opposite, I'm not sure, maybe I have here m equal -1, and you have complex functions, and here I talk about real functions. And maybe also I need to look at the chat. Avoid excitation of n not equal 1. I'm not sure that I got it right. So what is m not equal 1? For example, it is in case of electric dipole, m not equal 1. It's something like this. Maybe you will, I will draw an electric dipole. Here is m equals 0. And this is actually looks like this. This is electric dipole along the z-axis. Here is this guy, even, and m equal 1. This is electric dipole, which we have already seen along the x-axis. For example, sorry. It is like this. And this guy, this is along the y-axis. Also some kind of electric dipole. So what should we do to excite this electric dipole by a plane wave? Yes, exactly. We just need to change the direction of a plane wave and polarization of plane wave. And to excite electric dipole along the z-axis, we need to have incident plane wave polarized along the z-axis, and the same is true for any other. So to excite this guy, we need to have change the polarization of the incident wave, and so on. And in case of circular polarization, we need to, I would also like to note that this real harmonics can have only positive m, and complex harmonics can have also, so for these two, you have m from -j to j. And here, m is only positive from 0 to j. Just because here we have 2 instead of 1. This is cosine, this is sine. Okay, and then we move to the Mie scattering. And I would like to remind you that field inside the sphere can be as well as plane wave, as well as scattered field outside the sphere is, again, for x-polarized plane wave. incident along Z. In this case, field inside the sphere looks like this. So here, just sum over magnetic and electric vector spherical functions with some coefficients which depend on the frequency. And these coefficients actually have resonant nature, but they're not the same as coefficients in a scattered field. And here, we should also note that, as you remember, we have Bessel functions, spherical Bessel functions in the definitions of vector spherical functions. And for the field inside, we should put spherical Bessel functions. And for example, for a scattered field, we should put spherical Hankel functions, which this is just because these guys should not be divergent in the center of the sphere, and these guys should behave like an outgoing wave. And maybe you have already heard it. Okay. And here you, for example, see the plot of me scattering for a sphere with refractive index n equal 4. And here is just the comparison. This guy is a square absolute value of a coefficient before magnetic dipole function inside the sphere. And this yellow guy is outside the sphere. And you see that they are different. And our aim is actually assume that we know the field inside the sphere or inside any particle. And our aim is to find the field outside the sphere. And let us move further. Okay, and this guy, the coefficient inside the sphere just looks like this. Some Bessel functions, some Hankel functions, and this is Kr, and this is the same but with refractive index. So if we have field inside the sphere, now for further convenience, we will look actually at Z-polarized incident plane wave. So we have electric field component, and it is incident along y-axis, for example. And, oh, sorry, this is not true. What should we do actually to excite not Z component of electric dipole, but Z component of magnetic dipole? If we had K parallel to Z, if this combination gives us magnetic dipole along Y, what should we do to obtain magnetic dipole along the Z? Please answer in the chat. Yes, we have the right answer, two right answers, but not the only one right answers. For example, yes, we can do this. Or just like an option, this. It doesn't matter. So then we got it. We have field inside the nanoparticle in some shape of the form of all possible multiples. And we only interested now in this guy. This is magnetic dipole along the z-axis. And I didn't understand the question. Ah, yes, exactly. Sorry, here is X. And if we have a field inside the particle, we have polarization inside the particle, which is which can be written as epsilon as polarizability multiplied by field, and this is just a polarizability. And if we need to find a current, we need just to have time derivative of the polarization, and in a frequency space, it turns into this, I omega. So we have this formula, and so the current just looks like the same as the field inside, and it is already decomposed by multiples. And we can say that only in case of sphere, we can immediately say that only this guy will give some contribution in the magnetic dipole outside the sphere. It is just because the orthogonality of vector spherical harmonics, we cannot excite the, for example, magnetic dipole like outside fields by any of these remaining terms. So we will just forget about all this and consider just this term. And actually, we know how all these functions look like. You can find them in any book in the appendix. And this particular function is actually very simple. It has only one component. And actually, we can even draw this vector function. This is just like a circular currents outside around z-axis. They are all parallel to phi vector, and this is just the simplest vector spherical harmonic, and we can substitute now the current into the formula, into the main formula, just to obtain these coefficients. So all we need to do is to substitute this current here. And let us do this. Well, here is this formula one more time. And actually, you have a Matlab file called magnetic dipole. And this is, I think this is the time to open it. I will give you some time. And also I will send this file to Telegram if somebody has skipped it. And also here. And this is just one simple file. And what it contains, actually. It contains here just the parameters. You can, first of all, leave them like this, and then you can change it and look at something. And here you have a range of wavelengths. Here is from 200 to 100, and maybe it is already changed in file. And here, this is nanoparticle radius. This is refractive index of the media. And here, refractive index of the nanoparticle. So it can be, for example, silicon nanoparticle or something like this, because the refractive index of silicon is close to 4, but not exactly the 4. These are just parameters which depends on this, and you don't need to change them because they're connected with previous one. And here you have functions. Here this integral is written. So this is just this formula, and it computes two cases. By this function, it computes exactly the integrand of the approximate formula. So this function is just if you substitute your current here. So the spherical bessel function, you have replaced it by this guy. And your aim is to actually to write the similar function, very similar to this function. You only need to slightly change these guys, put them here, and obtain exact formula. And then you need to run the function, and you will have also the comparison with mis-scattering. And in case of exact formula, you need to have a coincidence with me theory. And also you can compare with mis-scattering using me calculator, but it is optional because here by what this guy just plots a result, an exact result to compare, and this should be equal to each other. And this will not be equal, and maybe I will try to start a poll one more time. For some reason it doesn't work properly. I don't know why. Maybe I would like to ask the organizers to make the same polls in the app, if you have time. And okay, I will repeat again what you need to do. Please open a file magnetic dipole, and you have a current. You have actually, you already know a current, and it is given by this formula, and you have substituted it in the formula in the frame. Actually, all this in PDF, and you can look at it one more time. And what is already written in this file is the integrand of the approximate function. So this is And here actually you have put it and here you need to put actually the same something like similar expressions and just but not approximate, but exact. And you will obtain the same integral, and after that you just need to run the file and look what happens. Where I define Cn00. This is actually the me coefficient proportional, and it is already given in the function. You don't need to change it. It's just this guy, but it is already given in the code. You don't need to do something like with this because it is part of the current. And D, you don't actually need this guy for the, because you compute the magnetic dipole. And that's why this is not given. And if in case if something went wrong, I will, after the practice, I will send all the codes with everything you have needed to do. I think I need to open the Matlab myself. Okay. Wait a minute. Have you run the function magnetic dipole? It should be computed, and actually you can run it, and it should work, I think. And give you this picture. And please, somebody write in chat if something works. I believe it should work. Okay, you only need magnetic dipole. The other file I will send later. Yes, you need to get the same plot. And here, yellow line is just me theory. And orange line is just computation by an approximate formula. You see that you have here some divergence with me theory, but here there is a coincidence, almost a coincidence, because it works. The approximate formula only works properly for big wavelengths. But your aim is to compute the same line by an exact formula. So you need to substitute your current into, wait a minute. You need to substitute a given current into this equation, and this what is done by, by this function. It should be done by this function, but this is now is wrong. You need to replace it by some expression. It is actually very similar to approximate formula. So you need to, you can do something like this here. But you need to replace here something to obtain the exact formula. Actually, I would like to note that this function computes the spherical Bessel function, which is dependent on x multiplied by refractive index. And maybe you should also use this function one more time to compute different type of Bessel function. And if somebody got the result, please tell me about it. Maybe it will be also more comfortable for you to look into PDF file. And I will just repeat one more time. We are doing this example with magnetic dipole, only with magnetic dipole. And Matlab code actually computes the formula 21. This is the integral, or the volume of a sphere. And you can see that this is actually a numerical integration in two cases, for approximate and exact formula. And the integrand, and this is the function which stays under the integral, and these are the limits of the integration for r, theta, and phi. So we are going to these two guys and look at them. And this is already the current, which we have substituted into approximate formula. And what is the difference between the approximate and exact formula? It's just in a Bessel function. So, one second. Actually, this function with approximate formula computes the z component of a b, where we put instead of Bessel function, it's limit, because r is small. So what is theta? Okay, David Zavogt found it, and it should precisely coincide with the result of a meteor. And actually, if you have found it, you can go. wait a minute. I need to open a few. Yes. Thank you for a finger. But wait a minute. This you have found the approximate result one more time. Masoud Hamidi. But you need that your blue line must coincide with the yellow line, not an orange line. You need to change something. No, it should not be the same. I will say what should be the difference. In approximate, you have these guys. Instead of spherical Bessel function, because it is just like this. And you need to replace this guy by a spherical Bessel function to obtain the exact result. And that's all, because the formula are very, very similar for exact and approximate. And I will tell you one more time how we actually compute three components, because the code only computes Z component, because we have Z-oriented magnetic dipole. So here you see, if you substituted the current of this form here, and this looks like, this is the current, and this is phi vector, and you have product of R and phi vector left, and for these spherical vectors, this product is equal to the theta. But you don't need to obtain the theta component of the vector. You need to somehow obtain this component. So, wait a minute, I will look at the chat. Yes, thank you, David. This is exactly what you need to compute. And I will send you one more file. And you can look the PDF further and actually make a second task, because it is written in a PDF, and I will explain the first task a little bit further. So instead of theta, you can put this sum. So to obtain x component of this vector, you need to compute the following integral. It will be proportional, because I have actually lost some constant coefficient here, but it is already written in the Matlab code. And x component will be proportional to the following integral. I just rewrite this guy. And then instead of, we put this, because it is what stands here before x component. So cosine theta, cosine phi, and then we put this further guys. Sine theta and one Bessel function and the second Bessel function. Okay, and then we can note that this integral will turns to 0. We can put it into Matlab or check it by hands, because this is just integral by the angles, by the angle theta, which make integral 0. And this is quite, can be quite obvious because first of all, we had only Z component of magnetic dipole, and we try to find X component. So, but we don't have X component in our problem. So this integral should go into 0. And the same problem will be with Y component. If we put these two guys back here, and we will get the 0 one more time. But Z component, and only this guy is computed in Matlab now, is proportional to the following integral. And here we put sine. And sorry, first of all. And here we put sine of theta, and then again sine of theta, and then two guys with Bessel functions. And this is expression is exactly what is written here. What should be written here. But in this function, there is different expression because we have actually in approximate form, we have instead of this Bessel function. And this is only the difference. And you can actually replace it. If somebody got the result, you should also tell about it. Or if somebody don't understand anything, you should also tell me about it. So here from Idris, actually, thank you for the picture. Here you have that your computation now one more time coincides with approximate formula, but you should change something in this function to your Z line should coincide with this guy, with me scattering. Okay. And Dmitry has sent me this file, and you see that it is exactly what you should have done. So this blue line and this yellow line coincide. Yes, Anton, I would like to mention it one more time, that if you use not the Matlab code, but this formula for cube, for cylinders, for any possible shape, this formula will work in case if you know the current. But the current you can get, for example, from a console, from a CST, and if you just put this formula somehow into console, and you did it actually yesterday with Ksenia. The next, for the guys who have managed to do this, you should open the PDF and electric dipole code and actually find two contributions, like in second task of the PDF file, which managed to find two contributions of the toroidal dipole and electric dipole. Actually, what's more, you should find an anapole. This will be you can try to answer this question, but for some reason I can't see the results of the Zoom question. You can try to answer it in chat or something like this. And also the organizers will put the same questions into the, I forgot the name of the app, into the app. And you can also answer these questions in the app after this lecture is already gone. And maybe for the correct answer, you will just get some additional points to the exam. So what is the anapole wavelength for this case, for the case of magnetic dipole? And the nanoparticle radius is 100 nanometers. Okay, for the earlier Matlab version, probably can be a mistake. Sorry, but I don't know. Probably you can replace the numerical integration by some other function for this. And probably you can also try to execute the electric dipole function or try to go into different version of Matlab, which is given by the lab. Sorry, I can't check it for the early versions of Matlab. And actually, in the start of the next practice, I will show what you should have done. So somebody can still try to do this during the break or something like this. And the second task is for those who already managed, is related to electric dipole. You have very similar code, but it's computed a little bit faster because all integrals by the angles are already taken. You can just check it by this formula. Here, all the derivations are shown. And here we just leave the integral over the radius of these bessel functions. And this is exactly what you see in the code on electric dipole. Only this integral is left. And so in case of electric dipole, you will actually obtain something like this expression under the integral. I will show it in the Matlab. Wait a minute. So here you have already two guys, approximate expression, and you have already the exact expression. So you don't need to compute the exact function yourself. And if we execute this code, we obtain the following. So this is the same as μ coefficient before the electric dipole. And you see that our exact computation coincides with μ scattering, with scattering coefficient we obtain from μ theory. And approximate integration, here you see a big difference for smaller wavelengths. And we are interested actually in anapole. And maybe you have already heard, or maybe not, that anapole is just a zero of the Mie coefficient in scattered wave. So where is the anapole? They're just here and here. There are many possible anapoles for any multiple, for any Mie coefficient, because the coefficient in scattering has many zeros. This is just a zero, and there are many zeros, and you have more for smaller wavelengths. And the aim that in case in approximate formula, you can actually compute contribution of the dipole and toroidal dipole separately. I will check this chat. Wait for a second. Yakov. Okay. Excellent. You got it. And now you see how simple just to transform an approximate formula into exact. So okay, thank you, Aksa. So maybe it will work for further versions. Many thanks for this comment. And here, Max also got it. Thank you. Actually, anapole, the definition of anapole can be just, this is just a zero of the scattering coefficient. And this is, I think, as for me, it is the simplest definition. So anapole is exactly these zeros. And yes, not the peaks, but the coefficient before some multiple, for example, magnetic dipole, electric dipole, any type of quadrupole, octupole, and so on. Sometimes that coefficient in scattering goes to zero for some wavelength, and this is the anapole wavelength. So, for example, some guys from our lab, Igor Gurwitz, and maybe you know him, he even can make particles where anapole of different multiples coincide. So you have actually zeros in many coefficients simultaneously. Thank you for the picture. Unfortunately, you have just zero here, but you need to make your blue function exactly the same as yellow somehow. And Ola, how many time I have?
10 minutes.
Okay, thank you. Maybe there are some additional questions. Yes, anapole is zero for total electric dipole. And then we speak about spherical multiples. When we speak about Mie scattering, we always talk about total electric dipole. And for this, for example, wait a minute, for the exact formula, then you have integral with Bessel function. We only speak about total electric dipole or magnetic dipole. Anapole can be not only for electric dipole, it can be for any kind of multiple. It's just zero in the coefficient. And if you take your approximate formula, and here you see we have, instead of Bessel function, we see these guys. So this is just came from the approximate forms of Bessel functions. You substituted here, and here, and here, and you obtain this formula, and you have actually two terms, which is proportional to the square of k vector here and here, and this is, and the second term is proportional to nothing, to 1. And if somebody managed to do this for early version of Matlab, you can send a zip file, and it will be very helpful. So, okay, and if you somehow just multiply these two guys, this and this by 0, you obtain only contribution of somehow simple Cartesian dipole. And if you multiply these guys, this one and this one by 0, you will have only the contribution of a toroidal dipole. There is a question to obtain contributions separately. Yes, it can lead to larger results than the exact. Each of term of a dipole and toroidal separately, just because they have different sign. You plot here the square of absolute value, but what happens then you have anapole? What should happen? In case of anapole, you will just obtain, for example, this will be a plot of total dipole. Sorry. And you will have then something like this. This will be plain electric dipole, simple electric dipole, I don't know how to call it. And there will be also another term, for example, something like this, but I'm not sure. That will be a toroidal dipole. So they will be not 0, both of them are not 0, but actually they are equal to each other. And what's more, they're different in sign, so they cancel each other, and that's why the anapole appears. Thank you. But here, I think I don't see the blue line. So maybe you're right, but something disappeared. So in case, actually I can do it. I can show how to plot the contribution of a toroidal dipole and electric dipole separately. Here you have an approximate formula. These terms, this guy and this guy, are proportional to k squared. Wait a minute. Oh yes, I will now compute it also here, and then you can compare. So I will just compute our approximate formula. It is just like an orange line. You see it has also anapole, so it turns to 0 here. And now I will just multiply this guy by 0 and this guy by 0. And here, green line is just a plain dipole because I put the toroidal dipole to 0. And now I want to put plain dipole to 0. So I multiply this guy to 0. and plot it one more time. So I got this blue line, and here blue line and green line are the toroidal and electric dipole, and I can look here closely, and you see that in a point of the anapole, they are just equal to each other, but the absolute value, only the absolute value are equal to each other, but the sum of them turns to 0. So that's why they give you anapole. Some questions in chat. Yes, you can find the multiple contributions using Matlab and CST. Maybe not exactly this code, but if you somehow extract your currents, if you have just a current inside the nanoparticle in any form, and you put your current into the formula from Ivan, so you will find the multiple contributions. Or you can put not your currents into Matlab, but your formula into CST or console. I'm not sure about CST, but I'm sure that this formula you can put into console, and you have actually already did it with Ksenia. Pavel, does anapole correspond only to particular multiple? So it would be anapole for dipole, but not for high multiples. Yes, exactly. Each multiple has its own anapole. And in general case, they are in different points, they have different frequencies. And only if you make a particle of some particular shape, some cylinder or something like this, you can make your anapoles coincide. Or in case if you have epsilon equal to mu, then you will have the coefficient for magnetic and electric multiples are similar. So in case if, I will talk about it later actually, and if you have epsilon equal mu, you will obtain similar anapoles for electric and magnetic dipoles. Is anything which is neither electric or magnetic dipole is called a toroidal dipole. I'm not sure about the naming of, I'm not sure that you should call it toroidal dipole this anything. You can probably call it toroidal quadrupole or toroidal octupole, but I think you should maybe ask guys, for example, Yegor Gurvis. I will maybe send his papers later in a chat. So some fingers. I will see. Yes, this is exactly what you should have done. What is the advantage of this method over the mean-theory calculations? The mean-theory calculations are valid only for spheres. And for spheres, there is of course no advantage. It's just the same. Well, what you do is do something like the same as me calculation. But you can apply this method to any possible shape of your particle if you have found the current somehow. And actually, the currents that you usually find numerically. But mean-theory doesn't work for other particles. It only works for spheres. What's the difference between what we did with Ksenia, the form of decomposition? I'm not sure exactly if you did exact or approximate formula, if you applied approximate or exact formula with Ksenia, but actually you did with her one of these cases. And in this sense, there is no difference. But actually, if you take a code from Ksenia and replace sphere, you can do it. You can replace sphere in a console by some cylinder, some ellipse, or something else, and you will obtain multiple decomposition just by the same formula. And maybe Ksenia applied approximate formula, and you can actually replace the approximate formula by exact. and you know now how to do it. It is very simple. One more question about cubes. Is it possible to use cubes on a substrate? Yes, actually it is possible to use on a substrate, but then you need to somehow understand, because you need to think about how to understand these results, because actually what is multiple? It is far field outside some particle, and this is a sphere should be in a free space. But if you have an infinite substrate, you will obtain some coefficients, but you will not can tell actually properly that these are exactly the multiples which you have in far field. But maybe you have already on a substrate, I think there was some slides of Andrei Yevlukin, if I remember it correctly. I don't understand why you only make the 1 0 and not the all these terms to 0. This just because of the definitions of the dipoles, because because x square is actually proportional to square of a wave vector, and toroidal dipole is defined like a something which is proportional to a square, and 1 is not proportional to a square. It's just because of the definition. You have 2 more files, and I think I'm out of time. Ola?
Yeah, we actually have 3 minutes out of time.
Okay, so we can just move further after the coffee break, after the lunch, I think.
Yeah, well, thank you very much, Kristina, and thank you everyone for active participation. Now we're having a break, and we will continue in 1.5 hours. So thank you, and see you here in 1.5 hours.
Maybe we can left this chat here and just...
Okay, I think you just leave it like this, and you'll check the task.
Okay, thank you. So, this evening. See you in evening.
Dear participants, it's time to continue our practice. Kristina, please, if you're ready, continue.
Yes. Wait a minute.
Yes, we are.
I need to switch. Okay. Now I start screen sharing. And the thing I wanted to show is that actually you have an algorithm to apply these formulas, and given by Ivan. And also actually this exact formula you can find also in different form like this. It contains vector spherical functions here, and in some cases you can also use this formula, but these 2 guys are just 2 different shapes of one thing, and the difference can only be in some constant here. And a basic algorithm to actually to solve any task you have is the following. You can take any object, you can take sphere, you can take cylinder, you can take any nanoparticle of any shape. Then you can find currents inside it. For example, in most cases, you can find it numerically with CAMSOL, for example. And then after, if you have currents, you can use the exact formula, substitute your currents here. And after this, you just obtain the contribution of each particular multipole into a scattering field. So, and actually you have already done it with Xenia. You have found the currents and the field inside the nanoparticle numerically with CAMSOL, and then you, I think you did the multiple decomposition by using the formula like this, or maybe you have used approximate formula. But this works just in a similar way because the formula are similar. Yes, I think, yes, there is a small typo in the 6th question on electrons. There you have number 7 on the end of 2 multiples, but it shouldn't be there. Yes, and okay, 270 nanometers. We should check it. And this in question 5, I think there is a typo, but in question 6, we can take n equal 1.5 and here equal 3 and compute. And then look what happens. Yes, and the thing that you should have done questions on event rocks actually like this. And here we have this picture, and I don't think that there is a mistake because here you can find an anapole for approximate and exact formula. Maybe you have put different values. And it was about not electric anapole, but magnetic anapole. I didn't mention it. Maybe that was the problem. So it should be like this. And now you just need to choose of these two guys. Okay, and you needed to do is to take your approximate function I need to open it. Yes. And here you see this this term is just a decomposed Bessel function. And let us put the same into exact function. And we need to put here Bessel function instead of this. So we introduce Bessel function. Let us call it like this. But here it should depend only on x without refractive index. And here, let us just multiply by this Bessel function and run the magnetic dipole function again. And it should be computed in half a minute. Okay, yes, exactly. This was about magnetic anapole, but okay, if you got 270 for electric, you're also right. And now we move to some different effect, which is called Kerker effect. Wait a minute. Because the following lecture will be, you will need it to understand the following lecture, and also this effect is quite simple and you can often meet it. So then you consider scattering by some objects. So, okay. Actually, then we have scattering problem. As I already mentioned, we always consider, and now we will again consider only field incident along the z-axis and polarized along x. Just the simplest case. And now what we have here electric dipoles, even electric dipoles with m equal 1. And here we have odd magnetic dipoles with, again, with m equal 1. And let us look carefully on these two guys, first of all. Actually, the Kerker effect was historically made not for this case, but for nanoparticles with epsilon equal mu. And I will talk about this effect later. You can find an original article of Kerker, Wang, and Gillis in the PDF. And okay, let us look at these two guys carefully. And let us go to the plane XZ plane. Question? How do you decide if the dipole is electric or magnetic? So let us look at these two guys. Look at the arrows carefully because they have similar radiation patterns, but here the arrows just go actually in here in X, Z plane, arrows are just like this. They go around this toroid, and so it is like such currents form a magnetic dipole. It's like a current loop or something like this. So it's quite similar. So the electric field of magnetic dipole looks like this. But the electric field of electric dipole goes along this axis. This is just perpendicular to actually it is always perpendicular to the field of magnetic dipole, and it's just goes along this surface. And in the similar plane, if you draw this, you can, this is M, and in the similar plane, if you draw this cross section, you have something like 8, and the arrows will go like this. And this is very important because let us look at the upper point and the bottom point. So here and here and here and here. And it is the similar plane. What happens if we just add this to this? Because they are vector fields, we should always summarize all these arrows as vectors. So in the upper point, we see that they look in one direction, and in the upper point, we will get a longer arrow, so the field in the upper point, electric field, will be bigger. But in the bottom point, let us look here. here is the arrow looking in the opposite direction of x, and here is the similar direction, so we got 0 here. Of course, it is in case of the absolute value is similar, but actually there's the same. So, well, and let us look at the similar picture. So here in the same case, we try to add up magnetic dipole and electric dipole. Sorry. And they're just perpendicular. And here, this is the z-axis, and this is x, because it was easier to draw. Okay, and here arrows are in opposite direction, and here arrows are in similar direction. So we got this kind of radiation pattern. If we draw actually the cross section, it will be something like a cardioid. So it is 0 here because arrows are in opposite direction, and it is multiplied by 2 in this point. So we have, if we summarize these two guys, we have something like forward scattering, and we have the directivity in our scattering. How to obtain, for example, backward scattering? So it is quite simple. We should put a minus sign before this guy, or between this guy. So we will just change the direction of all arrows in the opposite way, and we will have, and they will just add up in opposite direction. So we will have something like backscattering, but actually in real life, we never have just 2 multiples. We always have infinite number of some multiples, and actually in real life we can never obtain total cancelling of the forward scattering due to optical theorem, but actually we can in real life obtain total cancelling of the backscattering. This just happens for a following reason, that in a case of mu equal epsilon, we always have coefficient before the magnetic dipole equal to the coefficient before the electric dipole. And so they are always in phase, and they are always add up like this. Actually, it is not only true for dipoles. We have similar situation for any other multiples. So all the multiples add up like this, and they give total cancelling of backscattering. So this was the original Kerker effect. Let us try to find out which of these multiples can add up into some directionality. So which of these guys can give a difference between scattering along the z-axis and along minus z-axis? And actually, there are not all of them can do something like this. For example, let us consider electric dipole and magnetic quadrupole. And actually, here in magnetic quadrupole, these arrows are in opposite direction. So they're along minus x. In here, they're along x. And here, they're again along minus x. And for electric dipole, here they are along minus x. And again along minus. So in direction in upper point and in a bottom point, both of these guys have similar direction of the electric field. So they just cannot add up in some directivity. But if you take, we have already find out that if it add up these two guys, they give us directivity. Okay, let us move further and consider electric quadrupole and also electric quadrupole. Here we have again different direction of the arrows in the bottom and in the upper point. So electric dipole and electric quadrupole, actually they can add up into some directive pattern. And well, I will start a question. Be careful while answering it, and actually then we can move even further. We can look at the octupoles, and for magnetic octupole, these guys look in a different ways again. Actually, note that magnetic octupole behaves the same as in that meaning. It exactly behaves as magnetic dipole. So the direction of these two arrows is different. So it can add up with either magnetic quadrupole, either electric dipole to form the directivity. And electric quadrupole, it behaves in these 2 points in the same way as electric dipole. So it can add up with either electric quadrupole or magnetic dipole or magnetic octupole to form directive. So because actually you see that behavior is similar for these 3 guys, and for these 3 guys the behavior is opposite, and they will always behave the same way. So if you take further multiples, you always have the same behavior until infinity. And actually, but these guys are only m equal 1. And we need to find what happens if m not equal 1. Because we need to consider more general case. So let us look at this picture. You can also find it, for example, in Wikipedia, and arrows are also drawn here. So actually, you can also note some interesting fact about these arrows, because if you just take scalar spherical functions, these guys are just scalar spherical functions. These guys are also scalar spherical functions, and just draw an arrows from the just black, I don't know how to call this. So arrows from black to white parts of these guys, or even better, wait a minute. So from white to black, everywhere. You note that these arrows coincide with the direction of arrows on vector spherical functions. For quadrupoles, you perform the same. You do something like this, and actually you can, with this help, find out how vector spherical harmonics look like if you, for some reason, cannot find them. Okay, electric nature of electric magnetic dipole. Okay, how magnetic fields of these guys look like? Very simple. The electric field of a magnetic dipole is the same as the magnetic field of an electric dipole. So just change their places. So this will be, now this is electric field of the magnetic dipole, and this will be the magnetic field of the electric dipole. Very simple, and that's why I only talk about electric nature. So, okay, and magnetic dipole arrows are always perpendicular to the electric multiple arrows. And if we are talking about directivity along the z-axis, we can actually note that only harmonics with m equal 1 have intensity radiated along the z-axis. So here we have nothing. Nothing is radiated in z direction. Here also nothing is radiated in the z direction. Here again nothing. Here again nothing. And here, so there is something because m equal 1, and it is again always be something like this. So we have some radiation along z direction only if m equal 1. So none of these other guys can give any contribution to the directivity along the z direction. They can actually give contribution into directivity along different directions, but in case it can be a little bit tricky task because they have all different but actually you can solve any problem using you can always change your coordinate system and come back to this problem where you have multiple, when you have incident wave and your direction along z. Okay, and now you can find out which of them give contribution. The formula, and just looking at what I just said, you can derive a formula and also find them in many papers and books. It is just scattering cross-section in backward and forward direction. And you see both of them depend of all possible multiples. And here we say that here m always equal 1. That's important. And backward scattering is proportional to the difference of these guys and forward scattering to the sum. Actually, of course, if they're in phase, they give, for example, in dipolar case, then you can consider only dipoles, and they're just in phase because all the coefficients are actually complex. You will obtain forward scattering and if they are in the antiphase, so A equal minus B, you will obtain backward scattering more. So let us see at a particular example. Wait a minute. Okay, here we have scattering cross-section. You can build the same with me calculator. It is for silicon sphere of the radius 75 nanometers, but the picture will be absolutely the same for why would backscattering only count for m equal 1? Because for m not equal 1, these multipoles just don't radiate along z direction. And any directional scattering only computed for m equal 1. If you meant not the projection, but angular momentum, backscattering would not only count it for m equal 1, only in dipole approximation, but actually you need to apply this formula always to compute the exact value. So, okay, let us look at the scattering by a silicon sphere. Here we have magnetic dipole resonance, electric dipole resonance, and all the other multipoles are here absorption stars, so we don't see quadrupole properly and so on. And green line is just a square of the absolute value of the coefficient, and the same as for this blue dashed line. And these two lines are just phases of this coefficient. So here you see that it is pi over 2, and here minus pi over 2. And because of and in resonance, phase of this coefficient, of both of this coefficient is changed, just like any oscillation behavior. So, okay, let us look at this point. You see that both coefficient before magnetic and electric dipole are in phase, and moreover, but this is just a coincidence, they equal here in absolute value. And in this point, they are almost in antiphase. And again, they equal in absolute value. And let us look at the radiation pattern. For the first point, we have the in phase, so we have forward scattering. So most of radiation pattern is in forward direction. And here we have more backward scattering. Forward scattering, you can note, not totally cancelled, because we should not only use dipoles, we should also compute other multiples to obtain this. And okay, here we see backward scattering. And in resonance, we don't see that something dominates, because there is pi over 2 phase between them and very different absolute value. So we mostly see the magnetic dipole here actually. And so the same as here, we mostly see the electric dipole here. And it is X electric dipole and it is Y magnetic dipole. Okay, and here you also, this is from actually this paper. You can see the link in the PDF file. And here you have also forward to backward ratio. And you see that forward scattering is on the right side from magnetic resonance, and backward scattering is between magnetic and electric resonances. And then something again happens connected with different resonances, because not only dipoles give contribution. Okay, let us look at the results of the question. Most of you have answered. Okay, let's first answer. These two guys not give contribution into scattering because they don't radiate in these directions. None of these two. These two guys, of course, give some contribution, as well as these two, because this is just actually the same situation. And these two guys, you should note that here is both of them are odd, but we have actually okay. Paper link, you can find it in the PDF file I have sent you. It is in the same place as this figure. And here you can also find many other links on this topic. Most of them are very useful. Let us look again at these guys. Why, in the case if both of them are odd, for example, this one and this one does not contribute into radiation. Just because here the electric field is just perpendicular to this electric field. So they will just add up, but you will have something like this. Wait a minute. So you have this plus this, and you will have something like this in the upper point, but in the bottom point, you will again just obtain something like this. But you have different direction of electric field in the upper point and in this point, but intensity is similar. So these two guys cannot contribute in the directional scattering. Only if they have opposite parity. So here we put, actually, when we talk about dipoles, one of these guys should be along X and one of these should be along Y axis to give contribution into directivity. And the next question is, these guys give some contribution into directivity because they are, as I have shown, these two guys. So here we have arrows in similar direction, and here they are in opposite. And the last option is, from these 6 guys, maybe I should call them somehow. This is actually NE 1, and E2, 1, and E3, 1. And this guy is MO 1, MO 2, 1, and MO 3, 1. and any pair, one of them with a cross here and one of them with this bird here, any pair can give contribution into radiation pattern. So if we take, for example, this guy and this guy, they will give some contribution into a directional pattern. And the same happens if we take happens if we take these two guys. So actually it was quite a hard question, and the right answers are this. So all these four pairs can give some contribution into directivity. And you will have similar question on the exam actually, but with different multiples. And okay, actually we have some time for questions. So you can ask anything you want, because okay, I forgot to tell the important thing that here, if you consider some dielectric particle, here we have always mu equal 1 and epsilon equal, for example, 16 or anything. But in case if you consider mu equal epsilon, you will have that these guys are always coinciders. So A1 equal B1 in absolute value and in phase also. And A2 equal B2 and so on. So we will have always, not always similar absolute value, but always similar phase. And we always have totally forward scattering, because let us look not only at dipoles, because this sum will give us forward scattering. Let us look at these two guys. If we sum electric quadrupole and magnetic quadrupole, we have again opposite directions here and similar directions here, and they too give us again forward direction in case if they are equal in absolute value and equal in phase. And these two guys give us again forward scattering. Actually, okay, maybe just something went wrong here, but here we obtain that they give backward, but they should give forward. Okay. And that's all on Kerker effect. How do I know the propagation direction when look at spherical multiples of Wikipedia? You will only, these multiples are just spherical functions. Yes, and it does depend on situation. If you decompose, or if you solve your problem for the particular case of the X-polarized plane wave, you will have these guys in decomposition. Actually, in this case, you will have odd magnetic, and even electric. But if you, for example, rotate your incident polarization by 90 degrees and look at Y polarized wave, so you will have just opposite case. You will have odd electric and even magnetic multiples. But if you rotate your wave in any possible direction, you will have actually any multiple. You will, and this is because of this situation. This is because of the rotational behavior of spherical functions. Maybe for somebody who is familiar with, okay, one more question. Yes, in case if A1 equal minus B1 only backward scattering, but this never happens for real, for any real problems, because we just don't obtain this relation between these coefficients. So it's like unphysical. So on the rotation behavior of spherical functions, if we consider, for first of all, some scalar spherical function with particular, here J equal 3, with particular angular momentum, and for example, we want just to rotate it, to rotate the coordinate system, so rotate this function itself. So what is this function? And it appears actually from the group theory, because they are transformed as irreducible by irreducible representations of the SO3 group. And because of this rotated function is, you can always decompose it again as a sum of other spherical functions, but with the same angular momentum. Projections are different here. Projections can be any, but any rotated spherical function, scalar spherical function, you can write it as the sum of not rotated functions with the same angular momentum. For dipole case, it's quite trivial, while for question, even and odd modes look the same. Yes, the only difference between even and odd modes is that one depends on cosine and one depends on sine. And the only difference in radiation patterns is how are they rotated. You have here, they only depend on coordinate system, and even turns into odd one if you just rotate it by 90 degrees, and that's all. It really depends on this. Actually, what's more, it actually somehow reflects the behavior of the electric harmonics and the scalar functions, but only electric harmonics and the scalar functions under reflections phi into minus phi, because electric harmonics will be odd if they are odd, and scalar harmonics will be odd if they are odd under this reflection. But magnetic harmonics have opposite behavior. So for magnetic harmonics, letter even means that they are actually odd under such reflection. So magnetic harmonics always have opposite reflectional parity. And actually, as Ivan has already said it, because and under any reflections, magnetic and electric harmonics have opposite parity, and under inversion, which is called parity, also in the lecture, they also behave opposite. But electric harmonics behave the same way as scalar functions. And under rotation, both electric and magnetic harmonics behave absolutely the same as scalar functions. So if we take just scalar spherical functions with similar numbers, angular momentum and projection, and just rotate it on the same angle as scalar function, it will be decomposed by other vector functions. So if we take electric vector function, it is rotated function is decomposed into sum of different electric functions with similar angular momentum, and the coefficients are absolutely the same as for scalar guys. And the same, absolutely the same happens for magnetic function. So the rotation behavior of all three guys are similar, and actually the longitudinal functions also behave the same. And because of this, you can actually take the solution under some particular incident plane wave, and actually these coefficients are called Wigner-Dam matrices. But not for real harmonics, but for complex. Here, the real harmonics are drawn with sine and cosine, but to compute it properly, we should use these matrices only for complex functions. So if we know the solution under some particular plane wave, and it is like a sum of vector spherical harmonics with m equal 1. And if we want to find the solution under rotated plane wave, we can use this rule and just rotate all these guys and obtain our solution. It will not look beautiful anyhow, but you can actually find it using the rotational properties of vector spherical harmonics. Okay, this is the question. What I see is that the multiple at C3, 0 is replaced in the two equations. So what is the second equation tell us? I'm not sure that I understood your question correctly. Here, if you mean these two equations, okay, here this is the equation for scalar function, and this is the equation for, so this guy is actually this spherical function, scalar spherical function, 3, 0, but rotated. So this guy, and dependent on different, presented in different coordinate system, for example. But this guy is not a scalar spherical function. This is some vector spherical function, but with the same indexes. So it is, you can obtain it by a definition given in the beginning of the lecture. And it's just like a miracle that this is still represented as a linear combination of these guys. This is rotated by some angle, but these guys are not rotated. Yes, and it contributes itself here. Yes, and the right hand side, both equations. Right hand side, both equations have the same shapes, only actually, why are they changed? Oh, sorry. Okay, they're all just similar. And the point is vector spherical harmonics behave the same way as color. And magnetic also. Okay. And if you have some more questions, I can answer, because actually I have already told everything that I wanted. And if there are no more questions, we can actually finish. And maybe there are some questions related on a Matlab code. I have sent a version that should work for all the versions, so you can try to also, actually you can try to change some refractive indexes and compare, approximate an exact formula to see how they work in different cases, change range and so on. And I will actually send an algorithm if I find it. Do we need? No, I think you don't need to make a Matlab demonstration and final exam actually related to this practice. I don't know about Ilya Raskazov practice. Would we get the code related to this half of lecture? Actually, there is no code, but you can try to write something yourself. And actually, you can obtain some directivity, radiation pattern using Ksenia code in console, but you need to add far field module in console to see the radiation pattern, to compute the radiation pattern. How was the mode decomposition obtained in the last example? If you mean this example, it just me the same me calculator as given on our site. You can obtain the same picture, and phases I computed them myself, but you can build them, because actually you have these coefficients here in the code for magnetic dipole. You have this guy, and that solves scattering cross section for the me problem, just to compare the results. And here the me coefficients A, N, and B, N are computed. So for decomposition for spherical harmonic modes, I'm not sure which example you mean. Wait a minute. Okay, you can, if you mean these pictures, these pictures you can obtain from the Mathematica script, Wolfram Mathematica. Andrei sent it yesterday. And actually you can even change it. You can even change it a little bit to obtain the sum of the multiples. You don't need to remember them. You can always find them and just look at them. And actually, you can also obtain this radiation pattern using Andrei Wolfram Mathematica script. But you need to change it a little bit and compute not the multiples one by one, but the sum of two different. Is epsilon equal mu possible physically? Actually, why not? But I don't remember the material because I always do something with dielectric materials. Okay, thank you, Dmitry. In math materials, everything is possible, actually. Some more questions? How to plot forward and backward behaviors. If you have mathematical code from Andrew, and if you, I don't have it close, but this code draws only them one by one. So, okay, if you don't have them, you should learn any other way to plot vector spherical functions, or use console and just plot scattering by some particle. It depends on the last graph in Matlab. I'm not sure what you mean. This or this? This guy from the paper. Okay. This is not taken from the Matlab. This is taken from the paper. And actually, you can use, you can use the following way. You can take this formula and just substitute the coefficients into these two formula. I don't have a code, but you can write them yourself, because actually have formula, you have functions which are given in that file I sent you. You have functions for these two guys, and all you need is substitute this into to write this formula, and that's all. Yes. You have these me coefficients, they called A, N, and B, N, and you need to substitute it there, and you can plot them yourself. And also you can use, I don't know how this exact picture was obtained. It maybe was obtained with COMSOL or anything. In case of COMSOL, you need to evaluate fields in 2 points, in upper points and bottom points. And you also can use it, but it will compute longer time for sphere. And that's all. So, okay, I think that there is no more questions. And if there are any, I think you can write them to me by email or Telegram. And email is given in PDF file also. And good luck.